Hey everyone, we are starting probability, and the goal of this video is really just define probability, kind of break it down into little pieces, and have a good understanding of what random means in terms of probability. Okay, so we'll start off with just some vocabulary, really. The first thing we need to know is random process. What is meant by a random process in terms of probability? So random process is, or I guess it more so does something. It generates these things called outcomes. Generates outcomes determined purely by chance. So the perfect example of a random process, something that happens where we don't know what the outcomes are going to be, is again, just an example would be flipping a coin. Something that's happening by chance. Don't know the results of this, but it does have outcomes. There's two different outcomes in this random process. When you flip a coin, they would be, flipping it and getting heads or tails. Flipping a coin, not coins. That's it. That's what a random process is. So again, the outcome is what is generated. The outcome is simply the result of some random process. Fantastic. So for example here, you could just say getting tails. That's one possible outcome in our random process when you flip a coin. Just assuming we have a two-sided coin. You're either going to get heads or tails. I don't think a coin's ever going to land on its side. Fantastic. Getting tails is the outcome. So how often this outcome occurs really is known as probability. So let's go ahead and define probability real quick. Probability. Before we really get into definition, just one thing to make very clear with probability is it is 100%. It is a value. It is a value between 0 and 1. Has to be between 0 and 1. So a probability with a value of 0 would just mean that outcome is never going to occur. If the probability is 1, that means that the outcome is guaranteed to occur. Value between 0 and 1. That describes, it's a good word to use here is probably proportion. Proportion of times an outcome. So we're really looking at the portion of times an outcome occurs in a long series of trials. Long series of trials. What a definition there. So again, the value has to be between 0 and 1. And it's going to describe the proportion, like the likelihood, of times an outcome occurs in a long series of trials. So we're not going to have the answer of the true proportion or the true probability of an outcome unless we repeat this random process many, many times. That's all I'm referring to here. So I suppose one more thing we can do is say, well, a trial, what's a trial? A trial is one repetition of a random process. So hey, we got this random process here where we're like, we're flipping a coin. Each time you flip the coin and record the result of this outcome tails, that constitutes one trial. So to get the probability of getting tails, we would have to repeat this trial. We'd have to repeat this flip many, 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 many times. And after we do so, we'll know the true probability of that outcome. We'll go through a little web applet thing, and I think it'll be much more clear that way. But when you do talk about probability, this concept is going to get brought up. It is called the Law of large numbers. Another kind of complex definition, probably for a pretty simple concept. The law of large numbers is after many trials, after many trials. So this is really long run behavior here, not in the short term. After many trials, the proportion of times an outcome is successful or occurs. Maybe I'll say the proportion of times an outcome occurs approaches its true probability. All right, fantastic. So I'll explain this law of large numbers in a little example down here maybe. So let's say we'll go off with that same example. We're flipping a coin. And I'll just make a little chart here. Let's kind of segue nicely into the little applet that we're going to do. So we've got the proportion here. And we've got the number of trials down here. So flipping the coin, we know that we're going to either have heads or tails. So on, say, trial number 1, I flip the coin, it's tails. So there we go. It's like 100%. The probability is 1 there. So even though I flip the coin and it's tails, the true probability that I get tails is not actually 100%. It's not going to happen every single time. To see what the true probability is, I'll have to repeat this random process many times. And so maybe we, I don't know, we'll roll heads on the next one. So we've got tails like 50% of the time. Maybe we go on a streak where we get tails a bunch of times. We'll go on another streak where we get heads a bunch of times, which is bringing our proportion down. And eventually, this variability, in the long run, it's going to decrease and approach its true probability, which we know if we flip a coin, essentially we have a 50% chance of that coin getting tails. All right, hey, let me go to this on the web real quick. Yeah, it should be right here, maybe. Fantastic, almost there. Awesome, there's like things in my way. All right, hey, so we got this applet. Kind of the same scenario, just we're gonna look at the proportion of heads rather than the proportion of tails. So again, we know that the probability that we get heads on a fair coin is 0.5. 50% of the time, heads is gonna be face up. So if I toss the coin 1 time, okay, that's 1 trial. And it's 100% at this point. We rolled heads. But again, we can't say that the true probability here of rolling heads is 1 or 100%. We're going to have to do this many times. So even after 2 flips of our coin, we had 100%. On our 3rd flip, we finally got tails, which brings the probability down to 0.67. If I do this, if I repeat this random process many times, that law of large numbers says that we are going to approach the true proportion of getting heads. So I'll do it 200 times now. I'll hit toss. And you see, as this is going on, we're at like 150 tosses right now. The variability has gone down significantly. And we approached, if you follow this line here, we approached the true proportion, which I can graph now. You can see it here. By doing this, by repeating this random process many times, again, we approached the true probability. After flipping the coin 203 times, we now have a proportion or probability of 0.507. So again, I just want to make it very clear that probability deals in the long-term behavior, of this random process, not the short term. You see how much variability there was in the short term here. So never use probability to describe short-term events, only long-term. Suppose we could try this maybe like one more time. You can change the probability too that you get heads. So like we can change it to 0.7, but still the same thing is going to happen. There's going to be a lot of variability to begin with. And as the number of trials increases, we're going to see the true probability, or it's going to approach the true probability at least. You see, for a long time there, we were around 50%, but as we keep repeating this and keep repeating this, eventually this is going to get to 0.7. The more I do this, the closer we're going to get to that true proportion. You see, like we're pretty close now, 0.698, somewhere around there. Just to reiterate again, a lot of variability to begin with. So probability, not very good predictor of short run behavior, excellent predictor of long run behavior. If we do this many times, we can predict what's going to happen. You see this very incorrectly applied often. Like, give you one example that I can think of right off the bat. It's like a family. Family wants a boy. So the parents there get together, they make a baby, go to the doctor and ask him, like what gender is our kid? And it is a girl. All right, we'll try again. Go to the doctor, do a little ultrasound thing. Well, it's another girl. They try again, another girl. They really want that boy, so they try again, and they get another girl. So before they, family's getting kind of hectic there, 4 kids, a lot of diapers and arguments and fighting just all over the place. They go to the doctor before they have the next baby and they say, so what's the deal here? Are we ever going to have a boy? The doctor tells the family, well, of course, you've already had 4 girls. So, hey, the law of averages, this law of large numbers, this has to even out eventually. So absolutely have another kid. This one's almost guaranteed to be a boy. But this little assumption here is absolutely not true. Sure, if we took all the families, all kids born a year, the proportion is going to be pretty close to 50%. But in the short term, something as small as this, it's just not true. Again, that's known as law of averages. Another example is like you get a free throw shooter in basketball. He makes 90% of his free throws. And in this one particular game, he starts off with a miss, misses his next shot. The announcer's like, all right, guaranteed, this guy, he usually makes 90% of his free throws. So it's super likely that he's going to make his next shot, right? But that is not true. Totally possible that he misses 4 shots in a row. It's just as likely that he misses 4 shots as he, or at least what I should say is he has a 90% chance of making the shot, 10% chance of missing it, as he did on these ones as well. So beware of this law of averages. It's more of it's kind of like a myth, I guess. It's incorrectly applied to short run behavior. It's like when you're looking at the short run, tons of variability here, but in the long run, eventually things average out. So with something, a small sample size such as this, where there's only, you shot 4 times, or a small sample size like this, where we only have 5 children, it's not enough to declare a true probability. You need to repeat trials, again, many times. All right, so I hope you found this video at least a little bit helpful. Thanks for watching. I'll see you all in class. Bye-bye.